And again, welcome to today's webcast, Design for Availability. Our presenter is Brett Hollman, Solutions Architect for Amazon Web Services. Brett, you have the floor.
Thanks, Carrie. So my name is Brett Hollman. I'm a Solutions Architect with Amazon Web Services, and you are here to learn more about designing applications for high availability in AWS. We're going to talk today about best practices and things you need to think about when building a highly available application on AWS. So let's start off with talking about what is high availability. So high availability means different things to different people. So let's agree on some fundamental definitions to get started. HA, is also implemented differently based on app architecture and workload. So does HA mean that an app is simply live or reachable, or that it's servicing requests with an acceptable level of performance? Loss of availability, how do we define that? Is that offline or unreachable or partially available or slow to use? Do we include planned or unplanned? Probably. So our goal should be, no downtime and always available. So typically costs more to, make it app HA. There's a cost for HA. So, more cost probably, if you're building out your architecture correctly means, you've got a more highly available application. So a lot of people will talk about their app and say, we want to build an app to 4 nines or to 5 nines. Well, when you talk about 5 nines, you're talking about 5 minutes of possible downtime per year based on your SLA that you're defining. So to build an app that's more HA, incurs cost because you need to think a lot more about your architecture. And the last thing to note here is that, the higher the level of availability that you're striving for, the less likely it is that you can have human intervention in that. You need to automate your processes. You need to automate your deployments. You need to, source control all of your deployment code and so on, and thoroughly test that so everything is automated, and when you deploy, it's in a common fashion every time. So availability is related to a number of factors. Scalability is important to availability. So think about it this way. If you've got an application that doesn't scale and then your usage goes up, you're probably not going to be able to service users, proficiently or, with a good degree of success or a good degree of performance. You might have unhappy users. Fault tolerance is also, really key to availability. Building in fault tolerance at multiple levels of your app, making sure you're componentizing your app and building out components that are fault tolerant from each other, and that your app is fault tolerant to a particular component failing as well and fails elegantly is also an important concept. So AWS democratizes high availability. We provide multiple tools to build high availability out on your application. We provide concepts like building out multiple servers at your different tiers of your application, using redundant data centers, potentially even redundant regions, and using fault-tolerant services that are already available. There are a variety of different capabilities you have on AWS to build out a highly available application, and we're going to talk through those today. So first we're going to talk about AWS global infrastructure, so to put everybody on the same page. So first off, AWS is comprised of 9 regions, and a region is a collection of data centers in a metropolitan area. We have regions in North America. We have 3 regions in North America. We've got U.S. West Oregon, U.S. West Northern California, and U.S. East Virginia. And then we also have another region called GovCloud, which is an ITAR-compliant region for servicing government ITAR-compliant workloads. We also have regions in South America, Sao Paulo, Brazil, also in Ireland and Europe. We also have regions in Asia, in Tokyo, Singapore, and Sydney. So each region is made up of multiple data centers or a collection of data centers, and we commonly refer to those as availability zones. And there is a core difference. An availability zone is a data center or a cluster of data centers on a property or a piece of land. And each availability zone in a region, there's always more than one, and there can be each availability zone is built to be fault tolerant from the other availability zones in the region. They're typically segregated by 5 to 25 miles in distance. There is low latency redundant fiber connections between the availability zones. We try our best to build out these availability zones on redundant power grids and floodplains and so on to make these as fault tolerant as possible from each other. So when you talk about availability zones, you're talking about short latencies and the ability to build out applications that span multiple availability zones inside of a single region. Okay, so next I wanted to talk about the AWS platform stack and reference model. So if you think about building out your application on AWS or on any platform, there's a variety of tools you need. You're going to need your global infrastructure, your colos, where you put your racks and so on, your cooling, your power. AWS regions and availability zones fit into that block. And then there's also the networking that's required between your application. The connections to the internet, the connections to the other elements of your application or other servers in your architecture. And there's the servers, the storage, the database services you require. There's the application services like publish, subscribe, messaging, and queuing, and all of the other things that you use to build out a highly durable and redundant application. And highly available application. And lastly, there's the deployment administration tools. So AWS has services in each one of these areas that you can use to help build out a highly available app on AWS. So we talked a little bit about AWS having some building blocks that are fault tolerant right off the bat. So over on the left, we have these services that are inherently highly available and fault tolerant. Services like our simple storage service, or DynamoDB, where data is replicated around the region. We also have a couple of global services like CloudFront and Route 53. CloudFront would be our global CDN, our global caching network to deliver content to the eyeball. Route 53 would be our global DNS platform. We also have elastic load balancing, which would give you the ability to deliver and spread traffic across instances in a region or web servers in a region. Then we have a number of application-level services such as queuing service, simple notification service, simple email service, and simple workflow service, which provide you the ability to build highly available apps with fault-tolerant services that are built fault-tolerant right off the bat. You can use them right off the bat, and you don't have to build them on your own and deploy them on servers of your own and make them highly available. We also have other services that are highly available with the correct architecture. So services like Amazon EC2, our elastic block storage, our relational database service, and our virtual private cloud, if you deploy these services in the correct architectures, you can make them highly available. But on their own, each one of those typically are built and deployed in a single availability zone or single data center. So, we'll talk about the right architectures and how to deploy a correct architecture using these services to make them highly available. Okay, so here's a little agenda on what we're going to talk about today as we dive deeper. We're going to talk about designing for failure. We're going to talk about designing an application that spans multiple availability zones. We're going to talk about how to scale your application. We're going to talk about some self-healing things you can do with your application. And then we're going to talk about loose coupling for your application. And those are the 5 main topics we're going to cover today. So let's start off by building a highly available system. So we're going to start off by talking a little bit about what Amazon EC2 is. So Amazon EC2 it stands for Elastic Cloud Compute, and really what it is it's our virtual server in the cloud. When you launch an Elastic Cloud Compute or an EC2 instance, you're launching a server on AWS in the cloud. You're picking a region in a data center or availability zone that you want to launch it in, and we have many different sizes of compute, so you can choose one that fits your needs, with a specific CPU and memory and disk options. You can run Windows or Linux on it. You also have the ability to, when you launch an instance, you choose a machine image, or what's called an Amazon machine image, or an AMI, or an AMI, and you typically start off by launching a base operating system, AMI, so it might be Red Hat Enterprise Linux or Windows 2012. And then you go and you install your packages, you deploy your source code, you might start Apache up, and then you have the ability to create a custom AMI or a custom Amazon machine image that captures all those bits just the way they were, and you have the ability to deploy that and create new servers with it that would launch and have all the packages and source code deployed and Apache running and all of that. So Amazon machine images are a core principle. We're going to talk more about that later in the presentation. So when you launch a compute instance, you have full control. You are the root. You have the administrator rights. You have every EC2 instance is deployed in a security group with full firewall control that you have access to what you open up to the world and what you keep locked off. You also have monitoring and metrics that are pushed to CloudWatch or your EC2 instance. So those are some of the core principles about EC2, and we're going to talk more about each one of those as we go on. All right, so our base deployment is deploying an EC2 instance as a web server. Maybe loading with Apache and deploying source code on it. We might also start by deploying our database on there. As we want to, build out a little more durable, we would. Now we're going to launch a database server, and we're going to separate our web server from our database server. And to do that, we're going to choose Amazon's relational database service for this example. You can launch your own servers on EC2, your own databases on EC2. You can run a variety of different database technologies on your own on database or on EC2, but RDS gives you the ability to use our database as a service for MySQL, Oracle, or SQL Server. We'll talk more about RDS later in the presentation, but here's a good way to start. So then next we're going to deploy an elastic IP address to our web server. And what that gives us the ability to do is, the reason why we call that an elastic IP versus a static IP is via API or via the console, you have the ability to move that elastic IP address from one server to another. So let's say we're deploying an application, like in this case, and we've got a single web server. And let's say we've got an app that isn't allowed to horizontally scale. We can't run multiple web servers. The way the software, it might be a legacy app, it might be an older app. It has to run on a single instance. Well, we've got this elastic IP, and if that web server were to fail, we've got the ability to move it from one web server to another. And, we're going to next attach that elastic IP. We're going to spin up our Route 53 for our DNS. We're going to create an A record that binds www.mywebsite.com and points it to that elastic IP address. So, these DNS records will point your domain name to a particular IP address, which then sends the traffic to that EC2 instance. And then, again, that EC2 instance connects to the RDS database to serve up your database queries. So first we're going to talk about designing for failure. That was a pretty basic construct there, but we want to talk about designing for failure. So Werner Vogels, CTO of Amazon, said, in a variety of talks he's done, everything fails all the time. And I want to just point that out. I mean, hardware, data centers, network, databases, services, these things all fail. They're all known to fail. Nothing is perfect. There's imperfection in everything. So what's key is avoiding single points of failure in your architecture. You want to make sure each service is not a single point of failure. You want to componentize your service, and you want to assume everything fails and work backwards. Design each service as a black box, loosely couple services together, make each service highly available and scalable on its own, and then make sure your application can handle an individual component failing. And the application won't fail with an individual component failing. The application knows how to fail elegantly and still respond to the user, even though a particular component of a multi-component application architecture fails. So we're going to talk through those concepts as we go along, but your goal should be applications that continue to function no matter what. All right, so let's go back to our original example. We've got our DNS server pointing to our EC2 instance, which is then using RDS as the database. So let's talk about what happens if a web server fails. What do you do in this case? Well, we bound an elastic IP to it, so we have the ability to launch another EC2 instance and point that elastic IP address at that new EC2 instance. And that EC2 instance, when it launches, if we used a custom AMI that we captured that already had the database connection string and had Apache running and everything, when we launch that EC2 instance and attach the elastic IP to it, as soon as it's up and running, it has the ability to connect to the database and it starts receiving traffic from DNS. So you might have had a short downtime, but using the custom AMI and using the elastic IP address, we recovered pretty elegantly, pretty quick, maybe a handful of minutes of downtime. So that's not ideal, definitely not. But if we had an application that can only deploy on one instance, we're pretty good there. We did a pretty good job. Further, we could script the stand-up of the second EC2 instance and the move of the elastic IP address. Those things are all available via API. So you could write scripts that automatically, via alarming, we recognize that the EC2 web server went down. We may capture that message in a queue. that alarm that goes off, we may capture that in a queue, and we may have a server that responds and is watching that queue and says, oh, I need to launch a new instance, and I need to go and attach an elastic IP address. So we can do things in a semi-automated fashion. Or we could just have an alarm and have somebody respond to that alarm by standing up another EC2 instance. Okay, so let's talk about storage. Let's say we had storage that we really required on that last server, and we lost certain files in that last server. We want to do something that's a little more durable in terms of storage. So I'm going to talk a little bit about what elastic block storage is. Elastic block storage is our persistent storage. You have the ability to create a volume from 1 gig to 1 terabyte in size. You mount it as a drive to the instances. You format it. It's private to your instances. You have the ability to build this in a high-performant fashion as well. You can say, I want to run a very high-performant EBS volume, and you have the ability to provision I/O to the volume, how much I/O you want the volume to respond with. Also, one thing to note, these storage volumes, these EBS storage volumes are replicated within an availability zone. So when you provision an EBS volume, you're provisioning, let's say, a 1 terabyte volume of storage you're going to attach to an instance. There is a mirrored volume of that, and if your primary volume went down, you wouldn't recognize it, but we would actually move your requests over to the other EBS volume and provision another volume that mirrors it. So it is a little more durable than a single drive on the floor. Lastly, you have the ability to do backups and snapshots for those particular volumes and create a new volume from any one of those snapshots. So that's EBS in a nutshell. So now we're going to attach EBS to our particular web server. So now we have a persistent storage that lives outside of the web server. And if that web server were to fail at any point in time, we've got persistent storage that lives beyond the life of that particular web server. So let's say that that web server dies. What happens here? Let's say I've got important data that my web app requires. Let's say it might be logging that I'm storing or whatever the case might be. I need that data that's on that EBS volume to live and live on that, and be part of the service that, continues forward. So I got the ability now to, stand up a new EC2 instance. When I stand up that new EC2 instance, I can move the EBS volume and the elastic IP address over to that EC2 instance. And now I've got a little more availability built into my storage solution than I had originally. So, where we are right now, we're still in a very basic architecture. This is not something that's highly available, not scalable, but shows some of the starting points of how to build out a little bit more availability on your platform than running on a single server. So let's move forward. Okay, so next we're going to talk about Amazon Elastic Load Balancing. And Elastic Load Balancing gives you the ability to create a more highly scalable application. You have the ability to distribute or load balance traffic across multiple EC2 instances in multiple availability zones with Elastic Load Balancing. So a couple of features of ELB or Elastic Load Balancing, it scales automatically to handle requests. So as your traffic increases, it automatically scales out the load balancing as a service to handle your request volume. It also, is self-healing and available. It load balances across multiple instances and multiple availability zones. You have the ability to define health checks such that the instances it's serving traffic to, it can health check those instances, and if those instances aren't responding, it'll stop serving traffic to those instances. It also has the ability to use session affinity or session stickiness, where if you are storing session on a server, you can set up the ELB such that it always sends the same user to the same server instance where their session data is being stored. Now, we always recommend separating session from the server so you can scale out horizontally, scale up, and scale down your server, and you don't have to always send the same user to the same server. But if your application requires session stickiness, you can do that with the load balancer. Lastly, the load balancer does support SSL, and you can terminate your SSL at the load balancer if you choose. Okay. So, here's our base scenario. We're going to make our next step forward, and we're going to deploy Elastic Load Balancing. So now we're going to be able to scale out the web tier independently of the other tiers. We've got load balancing, We've got load balancing that scales on its own as a service. And now we've got a web tier that scales horizontally as well, so we can handle more load, and we can also handle the failure of our particular server. So, this is a much better use case than before. If a web server degrades or if we increase load, we have the ability to handle that load with ELB. Okay, so let's talk about ELB health checks and how we make this a little bit stronger. So ELB health checks allow you to drop dead or degraded traffic and no longer send it to instances that are that have passed away or that are expired or that have degraded to a point where they shouldn't be receiving traffic. So it's pretty easy to set up a health check on an EC2 or on the Elastic Load Balancing service. You simply define a file on your web server that's going to respond to the health check. In this case, we define check.php. And then that particular health check could just return a 200 OK, say, it might just return I'm healthy and return a 200 OK, or it could be a deep health check, and that is something that's recommended. That health check might reach down and make sure it can connect to the database, and it will only respond a 200 OK back to the load balancer once it's actually done a connection with the database. So, better practice maybe to do something like that. Then you can specify how long you'll give it to respond back. In this case, we're going to allow it 5 seconds to respond back. Next, we're going to say we're going to do a health check every half minute or every 30 seconds. And then we're going to set an unhealthy threshold. In this case, we set up five health checks. So if you fail 5 health checks in a row, we're going to deregister that instance from the load balancer and stop sending traffic to it. Further, if that instance comes alive again, it's going to have to respond 3 times healthy before we send traffic back to it. So we have the ability to set up an unhealthy threshold and a healthy threshold with the load balancer, and then how often we check it and what file we check it via. All right, so now our ELB is in place with supporting health checks. So how might that look? Okay, so now we've got an instance or a web server that degrades. What's going to happen in this scenario? So, what will essentially happen is that server is going to be health checked, and it might fail a variety of health checks. You have the ability to customize and use a minimum of 2 health check failures before you stop serving traffic to that. We set it at 5. After 5 health checks, it's going to be deregistered from the load balancer, no longer receive traffic, and then if that thing comes back to life and starts passing health checks, we'll start sending it traffic again. Okay, so let's talk about using multiple availability zones. So we built a scenario already where we have multiple servers to handle traffic, so we can survive a single server failing. We're using ELB health checks to survive that. But what happens in the event of a large-scale catastrophic event and a data center goes down? We want our application to be able to be fault tolerant across data centers as well. So let's start off by talking about the data tier and how we harden the data tier. We talked about using Relational Database Service, or RDS for short, and really that's Amazon's database as a service offering. We have Oracle, MySQL, and SQL Server database instances you can launch, and you choose which version of Oracle SQL Server or MySQL you launch, and it's going to create those for you. You actually, you can say I want to deploy MySQL 5.6 or SQL Server 2012, and it's pre-configured with sensible defaults to get you started. It's automated patching. We do all the disk striping and so on for you. You set up your backup schedule and your how long you want to save backups, and we'll automatically take snapshots for you in the background. And we stripe the disks. You can specify your I/O and performance requirements that you need. You can also set it up with failover capabilities, such that you can have a master running with a slave running in another data center and synchronous replication happening between them. And we're going to talk more about that in the coming slides and how you might utilize that to have a more redundant and fault-tolerant data tier on your application stack. Okay, so now we've deployed our application, and we've deployed it with RDS, and we deployed it with synchronous replication between a master and slave database. So you can see we're now running our application in multiple availability zones. We've got availability zone A and availability zone B, and we've got a master in availability zone A, and all the reads and writes are going to the master, and we're doing synchronous replication to the slave. So when we do a write to the master, it's automatically writing to the slave and then responding back to the server that initiated the request. Okay, so let's say that the database master fails. What happens in that case? Well, first, the slave is promoted to master, and then the connection string from the that was pointing to the master is then moved over to the slave. So you now have all of your web server instances pointing to the same connection string, which is now connecting to a different instance. So DNS is updated. It takes about 1 to 3 minutes for failover to occur. So the way we recommend you build your application out, putting in a back-off algorithm such that if you try to connect to the database and the database fails, you back off and then try again, and then you back off and try again. Eventually, it's going to come back if you're running in multi-AZ. It typically takes about 1 to 3 minutes before the new master is available and responding to requests. So that would happen. Then next, we'll stand up another slave, and we'll start synchronously replicating to that other slave back in availability zone A. And so your new slave is provisioned, and you're back in a highly available fashion within a few minutes, running multi-AZ on your data tier. So how hard is it to make these changes or to stand this up initially? It's very easy. I mean, really all you're doing is when you provision your database instance, you choose multi-AZ deployment, and that's all you need to do specifically to stand up a database in AZ-A and AZ-B and have master-slave replication. Very easy. This is supported on MySQL and Oracle right now for RDS. Okay, so we've got a data tier now that is resilient and fault tolerant across multiple availability zones. Let's talk about how we might do that on the web tier next. So we're going to use, this is the way our application stack looks as of now. We've got a redundant, fault tolerant multi-AZ RDS solution in place for the data tier, but we probably want to do the same thing at the web tier. So we're going to deploy the Elastic Load Balancer in front, and we're going to now send traffic to multiple servers and multiple availability zones. So we're actually going to have 2 web servers in each availability zone, and that load balancer is going to round robin the traffic back and forth across instances, and we're going to be serving web traffic out of each availability zone. And now each availability zone is going to point back to the master database to do its reads and writes. Okay, so now how do we handle scaling? So that's a great architecture. It's fault tolerant. It's a little more highly available, but if remember, we talked about scalability being a core tenet of building a highly available application and architecture on AWS. So what happens if my application requires scaling? Let's say I get to the point where I don't, I've got too much traffic coming in. I need to be able to respond to that, and my application needs to be able to grow. We want to be able to respond to that elegantly. We have a service for that. And so, this is the way our application looks right now. But Amazon gives you the ability to look at metrics, and you can look at those metrics via API or via the console, and the magnifying glass shows some of the metrics that are coming out of EC2. You can see the CPU, and you can see a variety of different metrics that are available to those EC2 instances via CloudWatch, which is our metric service. So CloudWatch plugs into auto-scaling, and it gives you the ability to scale up or scale down your compute or your web tier or your app tier or any tier of your application via compute metrics that are coming out of EC2. So we're going to talk a little bit more about that. So what is auto-scaling? Auto-scaling allows the automatic resizing of your compute cluster based upon demand. So the way it works, you define an auto-scale group. You might say, I want to have a minimum of 4 servers in my auto-scale group. I want to have 2 in availability zone A and 2 in availability zone B. And I want to scale up by increments of 2, and I want to scale down by increments of 2. And then you might say, you define a launch config, and that launch config would say, every time I turn up a new server, I want you to use this AMI, this custom AMI, and I want you to spin it up on a M1.extra large, and I want these bootstrap commands to be fired off on turn up of the instance. And so that's the way auto-scaling works. And then lastly, you define policies. You might define a scale up and a scale down policy. And the way you might do something like that would be to define a policy that uses CloudWatch metrics to scale up and scale down. You can further scale up and scale down based on a schedule. If you have a certain time of the day where your application always sees a spike in demand, and then there's another time of the day where that demand goes back down, you might set up a schedule to scale up at a certain time of the day by X number of servers and then scale down back when your load backs off. But if you want to do it organically based upon demand, you can define policies for scale up and scale down. And a policy might be something like, when my CPU layer on average hits 80% CPU utilization for over 10 minutes, I want to scale up by X number of servers. And then my scale down policy might be, if my CPU layer has utilization lower than 40% for over 10 minutes in aggregate, I want to scale down by 2 servers. So those are what autoscale policies might look like. So then you put those policies in action. And so here we're showing a picture of our web server tier, and it's now aware of the CloudWatch metrics. We're going to deploy auto scaling to that tier. So now we have the ability to scale up. And remember, without scaling, our HA solution could be dead in the water at this point if too many requests come in and we can't handle the traffic. So this is something that's good to have if you have an application that requires scaling, if you have organic growth in your application, or you have users at different times of the day, things go up or down. You can use auto scale by policy or auto scale by schedule to adjust your load. Okay, so now we've got an instance where our instances are heating up and they're hitting the policy to scale up. So how does that work? Well, the auto scaling policy fires and it starts launching an instance of a certain size or a certain instance type based upon a certain AMI you define, and again with any commands or bootstrap actions you want to take during launch of the instance. So now those instances start to deploy and are launched, and as soon as those instances boot and pass a certain number of health checks, they get attached to the Elastic Load Balancer and registered against the ELB, and they start receiving traffic. So now we're actually delivering traffic to 6 servers versus 4 based upon scaling on CPU utilization. Okay, so now we're in a situation where that spike in demand has gone down, and maybe it's late at night, maybe our application is slowed down, we're getting less traffic, and now our CPU utilization has been below 40% for over 10 minutes on average across our layer or our CPU or our web tier. So now we've triggered the scale down policy, and what happens is 2 of those instances are deregistered from the ELB, so they stop receiving traffic, and then auto scaling terminates those instances, and now we're back down to 4 instances. So again, this is where it's really nice to be not storing session data on your instances directly, storing it in another store like a database or a NoSQL environment or a caching layer, or potentially cookies or wherever it may be, but storing your session data outside of the actual web server so that you have the ability to organically scale up and scale down and not be abandoning sessions during that. Okay, so we're going to talk about scaling at the data tier. We talked a lot about HA at the data tier and being fault tolerant, but let's talk about scaling at the data tier and a few principles you might use to scale at the data tier. First off, RDS has the ability to push button scale. So you have the ability to scale up or scale down an RDS instance by going to the console and changing the size and hitting deploy. Again, you got a little bit of time where you fail. If you deploy in multi-AZ, you've got the ability to scale up one instance. You still are going to change the connection string and so on. So maybe a small amount of downtime. If you're doing this on a single instance, you're probably going to have a little more boot time. So maybe not ideal. So it's good to be running in multi-AZ where you fail over to a slave when you're actually scaling out. But you have the ability to scale up and scale down your instances, very quickly on your data tier. So you can now accommodate more reads and writes, have more CPU and RAM available to serve requests. You also have the ability to, if you're using RDS with MySQL, to scale out read servers. So where you've got a master slave on MySQL, you also have the ability to define read replicas, and you can create up to 5 read replicas for a master-slave combination on Amazon RDS. So you can find read replicas, and those read replicas are kept in sync with the master via MySQL replication. And now you can actually use the read replicas to point all of your reads from your app tier down to the read replicas, and then point your writes to the master. So you're taking your read load off of the master, and you're actually pushing it down to the read replicas, and only your writes are going against the master. You could also run all of your reporting and ETL against those read replicas just the same. Okay, so you want to optimize your master for all of your OLTP transactions, and the read slaves. You might point your table scans, your reporting to the read replicas. You can also resize the slaves, and you have the ability to take a slave and promote it to a standalone server as well. You also have the ability to just turn up a slave for monthly reporting if you want to, minimize costs. So, hey, I'm going to do monthly reporting at the end of the month. I'm going to stand up a read replica, replicate to it, do all my reporting, and then turn that slave down. So, good pattern there for saving money. Okay, so what happens when I've used RDS, or maybe I'm running my own databases on EC2, and then I hit the point where I'm running reads through another, through another mechanism. I might be using read replicas. I might have a caching mechanism in place for reads. But now my master is, saturated with writes. So, at large scale, you may run into issues with, database contention on writes to the master. So how do you solve that? Well, we're going to talk about 3 different ways you might look at that. First, we're going to talk about federation, splitting your database into, splitting your database up based upon function. Next, we'll talk about sharding, or splitting one data set across multiple hosts. And then lastly, we'll talk about, possibilities with MySQL or NoSQL. Okay, so first we're going to talk about database federation. So database federation is where you're splitting up database by function or purpose. So in this case, we might have had one database server running all of our forums, all of our user tables, all of our product tables. And now we're going to actually segregate those out and run those on different database servers. So we might have a master and slave and read replica combination for forums, another one for users, and another one for products. So, it is hard to do cross-functional queries now. You might have to do joins via code rather than things via SQL, but, this delays the need for something like sharding or NoSQL for quite a while and saves a lot of complexity you might incur with one of those other solutions. So, where this won't help with single huge tables that are growing out of control, this helps where you've got, reads and writes spread across multiple different areas like forums, users, and products. So if you do have a single huge table that's growing out of control, there's a variety of things you can do there. First off, we're going to talk about sharding. So what sharding is where I might have let's say I've got a really large users table, like in this example here. I've got a users table that's grown beyond the size that I can manage in one database. So what I might do is I might split that across 3 different databases. And then my application needs to be aware that maybe I've got users A through L stored in one database, and I've got users M through R stored in another database, and then I've got users S through Z stored in a third database, and the application understands when I want to go and write or read from a user in a particular, I need to go to a particular database, like shard A, shard B, or shard C. So there's really no practical limit on scalability here. You can create many shards, and there's a variety of ways. I articulated a very simple way of sharding, but you can also shard by function or key space. You can also shard with a relational database or NoSQL, and so very common that people shard out RDS or any of the RD BMS relational database services. You can also shard out Cassandra or Mongo or a lot of those other solutions and run many shards to achieve great scale at the data tier. Lastly, I wanted to just mention our DynamoDB product. It is a managed NoSQL offering, and you can grow your table to infinite scale on DynamoDB. You simply add data to the table, and we manage all the partitioning or sharding on the back end based upon the table size and about how many reads and writes you provision. And so you actually, with DynamoDB, you provision how much IU you want in terms of reads and writes per second. And as you turn that dial, we will repartition your data on the back end automatically for you so that it can accommodate the amount of reads and writes per second you require. So great solution for tables that are growing very fast. DynamoDB fills that category very well. Okay, so next we're going to talk about self-healing. So we talked about health checks and auto-scaling. And, we're back to our standard web stack with EC2 Autoscale and CloudWatch. Let's talk about how this might be self-healing. So, what happens if a node fails? How do we, hang on, excuse me. So what happens if a node fails? How do we prevent traffic from getting to it? So we set up a health check, and automatically ELB is going to recognize, that particular instance is not passing a health check, so I'm going to stop serving traffic, and then autoscale will recognize that particular instance is no longer viable, and it will terminate that particular instance. So autoscale is going to kill that instance, and then next it's going to start reprovisioning another instance. So autoscaling will recognize, hey, I'm supposed to have a fleet of 4. I've only got a fleet of 3. I need to launch another instance in availability zone B. So autoscaling starts replacing that instance in AZB, and then once that instance passes a number of health checks, again defined by you, it gets registered against the load balancer and starts receiving traffic again. So you can think of autoscaling in terms of scaling up or scaling down, but you can also think of it just in terms of maintaining a fleet. I might not be scaling up or scaling down at all. All I need to do is just maintain 4 servers. Autoscaling has the ability, in conjunction with ELB health checks, to maintain the fleet. So health checks plus autoscaling does equal self-healing, and that's a key point to think about. All right, so let's say we get into a situation where our application is in a degraded mode. The full app, we've done all these practices, but for some reason our application is in degraded mode. And again, everything fails like we talked about, but we've done a lot of practices now that should be guaranteeing that our application is highly available. But how do we want to respond if there was a scenario where our application goes into a degraded mode? So let's talk through that a little bit. Okay, so Route 53 has a concept called DNS failover. So you can set up a primary DNS route and a secondary DNS route. And then what we're going to do is we're going to stand up a static website on S3 as the backup route for our primary website. All right, so let's talk about how that looks a little bit. So this is a picture of the S3 console here, and here what we're doing is we're building out a static website as a backup in S3. So S3 can be utilized as a web server, and you can actually put S3, you can define an S3 bucket and set it up in website mode where it actually is delivering static files and actually acting like a web server for static content. So you can see here, you can set up an index document. In this case, it's index.html. You can also set up an error document, which is called error.html. And then lastly, you could have an about us, a contact us. You could have product pages. You can have all sorts of different content that's delivered statically from S3. So you could have a very nice little backup site that only in a totally catastrophic scenario would be used, but it would still actually provide a service to your users, might have contact information and so on. Okay, so how does this look? Well, so what we're going to do is we're going to go into Route 53 and we're going to create a number of record sets. We're going to create a record set for the CNAME for www.mywebsite.com, and it's going to point to our Elastic Load Balancer. So we're going to create a CNAME that points to our domain name, to our Elastic Load Balancer, and the routing policy is going to be failover routing. And lastly, we're going to define that first record that points to our app stack, our dynamic app stack, that's, again, fault tolerant and highly available. We're going to define that as a record type of primary. Next, we created that S3 static website, which gives a pretty nice user experience. Again, it's not dynamic, you can't log in and all of those things, but again, I've got my home page, I got my products pages, I got contact us, about us, all of that stuff in my static website. And I defined a routing policy of failover as well for www.mywebsite.com. But I defined a record type of secondary. So what happens? Well, in a case where the DNS Route 53, you set up a health check against your load balancer, or in the case where it actually can't send traffic to that primary route, it's going to actually push traffic to the secondary route. And then when that primary route comes back up, it's going to start sending traffic back to that primary route where to your load balancer. So this is a great way to back up your application. It's a little bit of a worst case scenario strategy, but you're actually serving users, so it works pretty well. All right, so on to our final topic, loose coupling. So important to build loosely coupled systems. The looser that you are coupled, the bigger you can scale, the more fault tolerant you can get. And so for those of you who haven't heard of SOA, SOA stands for Service Oriented Architecture, and really it means you're going to move services or components into their own tiers or modules. You're going to treat each of these as 100% separate piece of your infrastructure, so you can scale these pieces independently of each other. So Amazon.com and both Amazon.com and AWS do this. And if you think about Amazon.com, there are many components that make up the Amazon.com website. You've got recommendations engines, you've got reviews, you've got searches, you've got the web tier, you've got the products, and all these things come together to create a website. And all these things are components that are able to scale independently of each other. And if one of these things fails, you still have the rest of the website working. So the website's not going to fail because one piece of the website fails. AWS is the same. We've got each service inside of AWS represented by a different set of components. You've got different API endpoints for EC2 and for ELB and for all the different services. And then even behind the covers, AWS, componentizes each one of the different things you do, like, creates and reads and all the different things you might want to be doing. Building those as separate building blocks and having them scale out independently is a very key piece of, letting your infrastructure scale independently and letting, one thing not impact another. Okay, so, we're going to talk a little bit more about loose coupling. So the looser you're coupled, the bigger you can scale. It's important to, have independent components and tiers to your application. Design these tiers as black boxes, or these components as black boxes. Decouple interactions between them. Creating services layers between them. Favor services with built-in redundancy and scalability rather than building your own. We looked at the beginning at a number of services that offer, HA or fault tolerance right out of the gate with AWS. Great to use those. Don't build your own. Reuse what you can. One key concept there is Amazon SQS, our simple queuing service. So we're going to talk briefly about that. What it gives you the ability to do is define queues, and then via API you can place items in the queues and retrieve items from the queues and delete items from the queues. It's highly redundant. You can hit the queues from any of the availability zones in a region. Your messages are replicated around the region, so very durable. Unlimited number of messages, scales automatically. Great service to use. And let's talk about this particular use case where we've got a receiver that might be receiving something, might be pushing, then contacting a transcoding unit which then publishes and notifies. And, it's very linear. And these things point directly at each other. Well, a better way to do that might be to decouple these things by putting a queuing service in between. And now once the queuing service is in between, I can change the order of things. I can insert new processes in between. I can scale these the receiver route versus the transcoder route versus the publisher route separately. And, again, I can reorder my process and so on. So here's a real-world example of how this might look. I might have a user coming in, hitting a load balancer, hitting a web tier that scales out independently. Let's say that the user is posting a video. That video may put a message in a transcoding queue to respond to the user saying, hey, your video has been uploaded and submitted for processing. Then you've got a transcoding worker group that's working back on the backside, grabbing messages out of the queue, transcoding those videos, and then putting them into a different queue where then there's a batch, another set of workers that's grabbing that publishing queue and saying, okay, I need to go collect all the metadata and put it in DynamoDB and publish the assets in S3. And then once the assets are published, I go and flip the flag and turn these things on and make them visible to the users. And so then users can actually go and hit my website and see those particular assets available. So that might be a workflow, a possible workflow for a transcoding video delivery workflow. All right, so let's talk quickly about visibility timeouts. Well, let's say first, let's talk about what a visibility timeout is. So let's say I go grab an item out of a queue. I'm a transcoding worker. I go grab an item out of a queue. I'm processing that item, and all of a sudden I die. The instance fails. It degrades for whatever reason. Well, now in theory, I might lose that item. Okay, well, what the visibility timeout says is, okay, if you grab an item out of a queue and start processing it, and then don't go and turn around and delete the item, you set the divisibility timeout. In this case, we set it to 10 minutes. And in 10 minutes, that item will pop back into the queue since it wasn't deleted, and another worker node can grab it and process it. So I actually have some, again, this makes my transcoding process highly available. I'm not going to lose any items. If I don't finish them and delete them, they'll get processed by another instance. So how does that look? I grabbed a job and the transcoding worker fails, again, 10 minutes later that item pops back in the queue, in the transcoding queue, and then another worker is going to grab that item and finish processing that particular item. So, okay, that works great. Well, what about scaling for a back-end process? How do I scale a back-end process? Well, you also have the ability to scale out your fleet in EC2 based upon CloudWatch metrics from Amazon SQS. So you can use Amazon SQS CloudWatch metrics and auto-scaling to scale out your tier. So let's say your transcoding queue is just receiving a ton of requests. We've got tons of videos to transcode. It's very backed up. You can actually set up your back-end batch process of transcoding workers to scale based on the queue depth in SQS, and that's what you see here. We've scaled out many more workers to catch up, or over-provision to catch up and get back to normal, where our queues get back to a normal length, and then maybe we'll set another scale-down policy to scale down once our queue depth gets to a more reasonable level. Okay, so we've talked about a lot of concepts today. We've talked about design for failure. We've talked about multiple availability zones. We talked about scaling. We talked about self-healing. We talked about loose coupling. Let's just quickly review those and then wrap up. So design for failure. We talked about some very simple use cases, running a very single point of failure stack, but putting some means in place. Let's say we do have an application that can only run on a single server. We talked about a couple means for having persistent storage, being able to move your IP address, and so on. So this is, again, our base scenario. Then we talked about, okay, well, we want to be able to scale out and use multiple availability zones to be a little more fault tolerant, both at our web tier and our app tier. And of course, our elastic load balancing tier is fault tolerant right out of the box. And we talked about scaling out. We talked about scaling out at both the web tier and at the data tier. Then we talked about self-healing, using health checks in conjunction with autoscale to replace instances, deregister them, move them out, and turn up a new instance to replace them. And then lastly, we talked about loose coupling, using queuing, not building everything so it's point-to-point, using SO in your architecture. So given that, your goal should be building applications that continue to function and are survivable and are highly available. So again, it's all about choice. You've got to balance your cost with your availability, and come up with your own architecture. This is just an example of some tools that you can apply in a variety of different patterns to build a highly available platform that fits your cost profile and your RTO, and your RPO. All right, well, that's all I have. I wanted to provide a few links to our Architecture Center, to our articles, to our blog, and to our podcast. And given that, I'm going to turn it over to questions. So we've been collecting the questions you have. Okay, first, is EBS shared between AZs? Is it similar to RDS? So no, EBS is not shared between an availability zone. So when we talked about a couple of the services that can be used in a highly available architecture, it can be built highly available and fault tolerant. With EBS, you'd want it, an EBS volume is replicated within that AZ, so there is a backup volume for it, but it's within a single availability zone. It's not across availability zones. It is storage in a particular availability zone or data center. So it is a little bit different. Okay. So next, how can we take advantage of RDS master slave using SQL Server? Are there any built-in AWS services? So we have a great white paper on how to do that on SQL Server. I recommend going to aws.amazon.com/whitepapers, and it'll talk through running EC2 or running SQL Server on EC2 and actually using SQL Server always on availability groups. And deploying highly available SQL Server, using EC2 instead of RDS. But with SQL Server on RDS, you do have the ability to do point-in-time restore. So, between snapshotting and point-in-time restore, you do have some things that make it a more available solution. But to really get to that master-slave with automatic failover, please take a look at that white paper that I recommended over on aws.amazon.com/whitepapers. All right, let me look through the questions. What are the actual health checks? yeah, you can set them up as pings. You can set them up as HTTP gets and then a specific page. So like I said earlier, it is good to customize these. It is good to define a file and to use an HTTP get, and then have that file do a deep health inspection of your application, making sure it can hit all the individual components that are required. Or you might fail that particular server off if it can't connect to the database. And again, we showed the S3 backup, with the Route 53 failover, pushing everything over to S3 while the app stack is down. But again, use backoffs. Try to hit your RDS database. Keep on backing off, and eventually, if you back off, you'll hit the slave database. So is the ELB service considered highly available? Yes, it is. It's self-healing on its own, and it does scale out as your traffic scales. Can you have a load balancer with just one server in the beginning, or do you need two servers in order to configure the load balancer? No, you can. You can have a load balancer in front of one server. And if you want to deploy your app with one server to start, but you're going to scale it out very shortly thereafter, yeah, it might make sense to actually serve the traffic through a load balancer to start. You could also update your DNS later to point to the load balancer and then to the instance. So you could have your DNS pointing to an IP address for a single server, and then you could deploy the ELB in front of your EC2 instance and have it connect to your EC2 instance, and then you'd update your DNS to point to the load balancer versus the A record to the IP address, and then your EC2 instance is still serving traffic that's cached to the IP address, but as everybody starts recaching the new DNS records, your traffic will now point to the ELB and come in via that mechanism. Can you create reliable snapshots while an EC2 drive is being used? There are processes and best practices out there. We have articles on how to do that. If you look in the forums, there are good procedures on how to do that via the different mechanisms, on Windows or on Linux. So I'd recommend reading out there. Okay, so we're at the end of the hour. It's 10 o'clock. So I wanted to thank